Merhaba arkadaşlar. Bugün bir deneme anlatımı yapacağım. Bu elimizdeki araçlar ne kadar iyi çalışıyor onu görmüş olacağız. Okay guys, hello. Today I'm gonna talk about proportional integral derivative control, the PID lecture that we started the last time. We will see how the tool that I'm using to record my whiteboard is gonna come out. Okay, so let's start by writing down our title, which is proportional integral derivative control. Or PID control. So what we will try to do is to cover both the transient and the steady state analysis. Transient and steady state analysis. Okay, so what we will consider is the usual feedback structure. Where we have essentially a plant that is being driven by a controller that we label as GC of S. So the controller drives the plant, which is G of S, and the output is fed back to be compared with the reference input. Okay, so we have R of S here and Y of S over here. Okay, and GC of S for PID control has the general form when it includes all the components, is that it has first a proportional coefficient and then a derivative coefficient multiplied by S plus an integral coefficient multiplied by 1 over S. So these three parameters, Kp, Kd, and Ki, are the controller parameters for the general PID control. Okay, but what we will try to do is to take a look at these components one by one in order to see the different effects that they have on our system behavior. Okay, so let's start with proportional control. Okay, and let's assume that we have a plant model that is second order. Okay, so the plant model that we have is G of S given by 1 over S squared plus 10S plus 20. Okay. So for the case of proportional controller, our controller is a simple gain. Okay. So in this case, let's try some color. Okay. We have our specific block diagram is where we have only the gain as the controller and the given system plant as our plant model. Okay. Okay. All right. So what is the type of this system? The type is essentially a type 0 system, right? This is a type 0 system because it is a unity feedback system and we don't have any standalone integrators in the feed forward path. Okay, so the denominator of the feed forward or open loop transfer function does not have any freestanding S terms. Okay, so because this is a type 0 system, we know that ESS to a unit step input is essentially ESS equals 1 over 1 plus Kp, but this Kp is a different Kp. It's not the proportional coefficient of the controller, but this is our positional error constant. Okay, positional error constant. Okay, what is maybe we shouldn't use Kp for our proportional control, so let's maybe change this. Okay, so let's make this K rather than Kp, right? So let's put here K and K here in order not to confuse with the proportional error constant. Okay, so what is our Kp? Kp is by definition is limit s goes to 0 g of s, and that is basically limit s goes to 0 k over this g of s is the open loop. In fact, this is gc of s g of s, right? So let's correct that. K over s squared plus 10s plus 20. Okay. So what is this equal to? If we take s going to 0, these terms basically cancel out. And we have k over 20 as our Kp. And hence we have ESS that is equal to 1 over 1 plus k over 20. Okay, and that is equal to 20 over 20 plus k. So that is our steady state error. So what we mean by that is that because it's a positive number, okay, so what we will have is that if we apply a unit step input, what we will have as the output will basically look something like this, right? So we will have a second order response, and then the oscillations will stop eventually, and at the end we will have ESS, a positive ESS. That means the response will stay below the reference. Okay, we also see that for this type of a system, a type 0 system, basically the gain of the controller has an effect on ESS, and in fact if we increase the gain, the steady state error will decrease. Okay, ESS will be reduced, which is a good thing, by increasing the gain K of the controller. Okay, so we usually show this as such. If K is increased, ESS will be decreased. Okay, so K is the design parameter of the controller, and ESS is the resulting performance parameter. Okay, so so we see that the gain has a positive effect on the steady state error, but is there any consequences to that? Other consequences. Okay. For example, what happens with the transient behavior? Okay. So in order to find the transient behavior, we need to look at the closed loop transfer function, the overall transfer function. In particular, the denominator that will give us the characteristic equation, and therefore the poles of the system. So let's calculate the transfer function. The overall transfer function is, well, we have the open loop here, GC of S, G of S, divided by 1 plus GC of S, G of S, because we don't have any block on the feedback path. Okay, so for our case, this is going to be K over S squared plus 10S plus 20, and divided by 1 plus K over S squared plus 10S plus 20. Okay, and that's going to become K. Well, we will multiply with the denominator both of these terms, and then we will essentially simplify the denominators. So I will have here, sorry about that, let's erase that, S squared plus 10S plus 20 plus K. Okay, now in order to be able to analyze this, we have to make an assumption, because we have only studied the transient response of second order systems having the standard form. The standard form was omega n squared over S squared plus 2 psi omega n S plus omega n squared. So in the standard form, you can see that you have this term equal to this term, but in this case, we have K in the numerator, but 20 plus K in the denominator. Okay. So we will assume the standard form and only consider the denominator of our transfer function. If you want to give further detail, you should basically say, assuming that K is somewhat larger than 20, we can do that. Okay. 5 to 10 times larger is usually the norm. Okay. So what happens as we increase K? Okay. K is increased. Okay. We see that 2 psi omega n is equal to, in our transfer function, is equal to 10. That means psi omega n is equal to 5 and is constant. Okay. But we have basically omega n squared is equal to 20 plus K. So as K is increased, omega n is increased. Okay. So if we want to sketch the pole zero diagram, we see that basically psi omega n, which is the real part of the poles, psi omega n, is equal to, so minus psi omega n is equal to minus 5. So this is constant over here. But as I increase K, okay, I'm basically moving away from the origin. Okay. So as K is increased, we can see that this is J omega D1. This is J omega D2. So that means omega D is increased. Okay. Obviously, the complex conjugate happens over here as well. Okay, so what's the effect of that? First of all, if this is our theta 1 and if this is our theta 2, we see that as k is increased, omega d is increased, also theta is increased. Okay, so omega d increased means faster oscillations. So frequency of oscillations increase. And as theta is increased, right, we have, if theta is increased, we know that cosine theta is decreased, therefore psi is decreased. And that means MP percent increased. Okay. Please remember how the maximum overshoot relates with psi. Okay, if we sketch MP percent with respect to psi, right, it starts with 100% and then goes down to 0 as psi ranges from 0 to 1. Okay, so there is an inverse relationship between psi and the maximum overshoot. Okay. Also, we can also comment on other parameters. For example, the peak time, the time where the oscillations, the first peak happens in the oscillations of our system is given by pi over omega d, and this gets smaller. Okay, so peak time decreases. So is the rise time, because it has also a relationship given by pi minus theta over omega d. You see that theta increases, omega d increases, so theta has a negative sign. So it's going to decrease the numerator, and also the denominator increasing decreases essentially the term. So TR also goes down, as well as TD. Sorry, not TD, TP. Okay, the peak time. Okay, so TP also decreases. Okay, so if we sketch these two systems, right, as I increase KP, as I increase the controller gain K, essentially we have an exponential envelope that stays the same because psi omega n product stays the same. But if this is your initial system, right, that's going to have essentially a damped sinusoid like this. As we increase K, what we will have is that we will have a system that will have a faster rise time, so smaller rise time, faster oscillations, but it's gonna be bound within the same envelope. Okay, so this is our system 2 and this is our system 1. Okay, so this is our system 1 and this is our system 2.